This is a lesson that, quite frankly, many semesters have gone by where I haven't even taught this lesson. Sometimes I teach it, sometimes I don't. I feel as though I would like to this semester to give you a bit more of a leg up, so to speak, on post-secondary. Because sometimes when I talk to students and they go to post-secondary and they talk about learning about the second derivative test, they're really confused because the second derivative is used to determine intervals of concavity. That's all right, Dan. I'll explain it again a little bit later. So this is called the second derivative test, but right out of the gate I want you to know that this has nothing to do with concavity directly. We're not talking about a second derivative table. We're actually going to be using the second derivative to find out maxima and minima, which is really strange. It's called the second derivative test. It actually uses the first derivative and the second derivative. So as a warm-up, we're going to go through the meaning of a function, its derivative, and the second derivative by looking at this graph. And it seems to me, I don't think those Roman numerals are on your handout, so you'll want to add them, 1, 2, 3, and 4, to your graph. And what we're asked to do is fill in information regarding those points. So when I take a look at the column f of x, don't forget that f of x is y. And when you take a look at point 1, and you take a look at point 2, and you take a look at point 3, all three of those points are above the x-axis, which means that the y-coordinate for all of those points is positive. So f of x at point 1 is positive, f of x at point 2 is positive, f of x at point 3 is positive. When you take a look at point 4 lies below the x-axis, and that means that f of x at that point is negative. This first column of what we're completing here has absolutely nothing to do with the second derivative test, which we're going to learn about in a minute. It's more about the next two columns. So what do we know about the derivative at point 1? Well, the tangent at point 1 is 0. The tangent has a slope of 0 at point 1 because it's a maximum value and the derivative is defined there. When you take a look at point 2, the derivative at point 2 is also 0. It happens to be a minimum value and the derivative is defined there. Now point 3 is a maximum point, but the derivative at point 3 is undefined because point 3 is what we call a cusp. And I'm just going to draw below the graph a cusp. So that's what I'm talking about when I refer to a cusp. And when you look at the slope of the tangent on the left-hand side of that point, the slope of the tangent is defined to the left, the slope of the tangent is defined to the right. But if you look at the slope of the tangent as points get closer to that cusp, the slope of the tangent on the left and the slope of the tangent on the right are going to be different, so they're not approaching the same thing, which means in terms of a secant approaching a tangent, that limit as the slope of the secant approaches the point where tangent is defined, that limit doesn't exist because the left and right hand limits are different. So I'm just reminding you that at a cusp, this is what we refer to as a cusp, the derivative is not defined. What about at point 4? Well, at point 4, the derivative is 0 as well, because the slope of the tangent is 0. And you know, maybe what I can say to you right now is that for max mins, the derivative will be 0 if the derivative is defined there. Maybe that's the best thing I could say to you right now is If the derivative is defined at a maximum or at a minimum, the slope will be 0. Now, what about the second derivative? Well, I'm going to jump to point 3 and say that the second derivative is not defined. And we haven't really talked about this in detail, but I will tell you right now, any place the first derivative isn't defined, the second derivative cannot be defined. It's maybe something that you can just remember. It's really difficult for me to explain why that point 3, has an undefined second derivative. So I'm just going to leave it at the fact that if the first derivative isn't defined, neither is the second. Now, what about the second derivative for points 1, 2, and 4? Well, this is what we just learned. We learned that if you take a look at point 1, since point 1 has a concave down shape to it, the derivative, the second derivative at point 1 will be negative because it's concave down. Whereas in the region where point 1 is, it's concave up. In the region where point 4 is, it's concave up as well. And that means for concave up that the second derivative is positive. So I think what this exercise, this warm-up, is intended to do, was my original intention, is to get you thinking about what it means to say a derivative is positive or a second derivative is negative, those types of things. Let's talk a little bit more about point 3. Point 3 obviously is not concave up, and point 3 obviously is not concave down. On the heels of what I was going to explain to you, Dan, about inflection points, an inflection point occurs if the second derivative is 0 at times, where the concavity changes. And the concavity at a cusp doesn't change. It goes from concave up in this case, and it continues to be concave up. So one way for you to think of the second derivative not being defined there, although it's not important for this lesson, is to say that the concavity doesn't change. Okay. If the concavity does change, then it's an inflection point. Okay. So now let's talk about the second derivative test. So when you graph functions, any point where the first derivative equals 0 or is not defined are considered potential maxima or minima. And that's the point of finding critical points of the first derivative. The point of doing a first derivative chart is so that you can find out which of those critical values are in fact max or min. Remember, not every point where the derivative equals 0 or is undefined is a maximum or minimum. You need a chart to do that. Now, we've called that the first derivative test. That's what they call it. The second derivative test is also used to determine max-mins. Okay, so there's a problem with the language here. What we were doing yesterday and at the beginning of today, which was finding intervals of concavity, is using the second derivative, but that's not the second derivative test. That's just a second derivative analysis. So the second derivative test is used to find max-mins, but it's limited. The second derivative test doesn't always work. Okay? So if you want to find max-mins, one way that will always work is to use the first derivative test, which is find the first derivative, find the critical values of x, set up a first derivative table. Another way that you can use to find max-mins is the second derivative test, but it works sometimes and it doesn't work other times. So why would we use it if it doesn't always work? We use it because when it works, it's easier. All right? So when can we use this second derivative test? We can use the second derivative test whenever the first derivative is equal to 0. We cannot use the first derivative test for cases where the first derivative is not defined. Okay? And particular functions at max-mins always have first derivatives equal to 0. I'm aware this is difficult to follow, but I'm hoping that it's going to all gel together in a second. Specifically, polynomial functions are ideal for the second derivative test. You can get all of the extrema, and you can do it very quickly. So here's the second derivative test. And again, it relates to the first and second derivatives. This is going to require some thought on your part. If the first derivative equals 0, and the second derivative at that point is positive, then there must be a minimum at that point. Okay? So just to show you this, there's a graph at some value of c, and if I said to you, what is the derivative at that point, you would look at it and say, well, the slope of the tangent will be 0, so the derivative at that point is 0. If I said to you, what is the second derivative at that point, you would look at it and you would say it's concave up, so the second derivative must be positive. This is one of the reasons why we did that warm-up, is so that you can identify whether derivatives or second derivatives are positive, 0, or negative. So look at what we're saying. The slope of the tangent here is 0, and it's concave up. How on earth could you draw a graph that has a slope of a tangent of 0 at a point and concave up unless you drew it that way? Which means that's a minimum. There's a minimum at x equals c. There's no other way you could draw a curve with a horizontal tangent, which is the first derivative 0, so that it's concave up and not have a minimum there. So that's one half of the second derivative test. The other half is the opposite. What if the first derivative is 0, but the second derivative is negative? Well, if the second derivative is negative, then it's concave down. And that leads us to the conclusion that there must be a maximum there. If you take a look at the point where c exists on this function on the right, the first derivative is 0 because the slope of the tangent at that point would be 0, and the second derivative is negative because it's concave down. So that's a local maximum. And that's what the second derivative test involves. Any questions so far? All right, if we go back to our warm-up, I want to point out that those 4 points that I chose are all max-mins. All of them. Point 1 and 3 are maxes, and point 2 and 4 are mins. If you take a look at point 1, what we said about the derivative was the derivative equals 0, and we said that the second derivative was negative, and according to the second derivative test, that's a maximum. For points 2 and 4, what did we say about both of those points? We said that the derivative at each of those points was 0, and the second derivative was positive, and the second derivative test says those are minima, and in fact they are minima. Now, if you go to point 3, those are two right. Those two things are right. The second derivative test works there. But if you go to point 3, what did we say about the first derivative? We said the first derivative is undefined. Okay, that means the second derivative test is not going to work. Because if the first derivative is undefined, you're automatically in a different lane than the lane that deals with the second derivative test, because the first part of the second derivative test says the first derivative equals 0, and the first derivative at point 3 is not equal to 0. So the first derivative is not equal to 0, it's undefined, which means the second derivative test doesn't work. So for a point like that, you would need to use a first derivative chart. But basically, since polynomial functions never have cusps, polynomial functions can always be analyzed using the second derivative test to find max-mins. Any comments or questions now before we do a couple of quick examples? This can be confusing, so let's try a couple of examples now. Use the second derivative test to find all extrema in each case. Okay, this function is polynomial. We know even from Math 30 that this polynomial function will look something like this. Get a pen going here. It will look something like this because it's odd. The right arm goes up because the leading coefficient is positive. So what we are looking for are the coordinates of any max-mins. And we know from experience that with a polynomial function, a max will always have the first derivative at x equals c equal to 0. The second derivative test is going to work here. So how does it work? We find the first derivative, which is 6x squared minus 6. We find the critical points by factoring. We get f of x equals 6 times x plus 1 times x minus 1. So the critical points of the first derivative equals 0 at x equals 1 and x equals negative 1. Are you fine with that work so far? No questions. So what we're going to do is the following. We're going to make a chart, well, not a chart, a table of values where we have critical values for the first derivative, and then we have the value of the second derivative at those critical values. In other words, we're going to take that 1 and negative 1 and put them into the second derivative and see what we get. So we need to know the second derivative. Well, if this is the first derivative, the second derivative is 12x, which is pretty simple. And here's the important point. I don't care in here whether what the second derivative equals. All I care is whether it's positive or negative. And if I were to put the critical value of x for the first derivative into the second derivative, I will get a positive second derivative. And if I put negative 1 into the second derivative, I get a negative second derivative. What does this mean? It means at 1 comma something, there's a maximum because, there's a minimum because it's concave up. That positive for the second derivative means it's concave up. So it must be a minimum. At negative 1, it's concave down. Well, concave down looks like this, so there must be a maximum. And then all you have to do is find the y coordinates. So if I put 1 in for x, you go ahead and calculate the y coordinate when you put 1 in for x. And confirm that you get 9. Anybody else get 9 for y? Perfect, thank you. And then go ahead and put -1 in. And confirm that you get 17, but I really need confirmation on that. I think it's 17, but yep, good. Thank you, Julian. Now, let me just say at this point, there are going to be some people who will never see that the second derivative test is easier than just doing a first derivative table. I understand that because it's confusing. You're using the second derivative to talk about max-min. You would never be expected to find max-min using any particular algebraic method. The algebraic method would be up to you. Let's try one more, though. We're going to need to find the first derivative, and we're going to need to find the second derivative. The first derivative is 8x cubed minus 3x squared. The second derivative is 24x squared minus 6x. Please double check my work there. I think it's fine. I'm not a big fan of working left to right, but I'm going to do so anyway. Can factor out a 6x out of the second derivative. You know what? I don't think we need to factor the second derivative. Let me explain the reasoning why we don't. What we are doing is we are factoring the first derivative so we can identify the critical values of the first derivative. In fact, you know what? It's not even the critical values of the first derivative. It's the zeros of the first derivative. These have to be numbers that make the first derivative 0 in the second derivative test. And the numbers are 0 for the x and 3/8 for the 8x minus 3. And then the second column is simply whether the second derivative at those points is positive or negative. So we put in 0 for x in the second derivative, and we get 0. Okay, just a second here. We got 0 for the second derivative, and that means that at that point, where the slope of the tangent is 0, at that point, it's neither concave up nor concave down. Well, what does that tell you? It tells you it's not a max or a min. We'll get to what that looks like in a second. When I put 3/8 in, I would recommend just crunching this on your calculator. Go ahead and put 3/8 in for x. 3/8, I believe, is 0.375. You get a positive number. So this is telling you that it's concave up, and since the derivative is 0 at that point, there's a minimum at 3/8. This is telling you it's neither concave up or concave down, and that's telling you that there's no max min there. And this is where I have to probably agree with most of you. I think the second derivative test is really not that informative. If I would have done a first derivative table and a second derivative table, I might have gleaned more information about the function. I suspect that at that point that we're talking about, whether it's neither concave up nor concave down, it's an inflection point that looks something like that. So if you did a first derivative chart, you would find that the function is increasing and then continuing to increase. Anyway, we can take a look at this. By the way, if you want to find out the y coordinate, you can put 3/8 in there. I really don't care what it is, but you can put it in. Let's take a quick peek on our graphing calculator at what this thing looks like. It's 2x to the 4 minus x cubed. This is definitely a case, everybody, where if you used simpler math like polynomial rules from 30-1, you'd get a quicker, better picture of the graph. But let's take a look. I'm going to go zoom 6, then have to adjust it, I'm guessing, because it will be quite steep. Okay, interesting. There's something going on in there. I take it back. I think you would definitely need to do a full calculus analysis here to decide what this graph looks like. Because it is quite involved. There's something else there. I'm going to zoom in even more. This is going to be subtle. I'm just going to zoom into this little slice here. And unfortunately, I can't just hold the key down. There's that minimum. Yeah, so math 30-1 wouldn't reveal all of that. There's that minimum at 3/8 comma f of 3/8, and at x equals 0 at the origin, it's not what I drew on the board. I drew it backwards. It should have been the other way around. It should have been that way, but you get the idea. Look, if you want to use the second derivative test, trigonometry. I don't have the questions here right now. If you want to use the second derivative test to answer those questions that are on page, I think it was 224, 232 rather, go ahead. If you want to do a full-blown first derivative chart, you can do that as well. It's up to you. Where we're at now at this stage of the game is you're using all of the skills available to you to analyze things graphically. Does anybody have any questions with that last example? Okay, so it's 2 o'clock. You've got some questions to work on. I'm not in a big twist about you hanging around here today. If you need to, you can. If you want to, you can take off now. I'm still going to mark you present. Just be sure that you get 2 things. You get your assignment into me if you haven't already done so by 4 o'clock. And you get a good handle on everything that we've covered so far in Chapter 5. So that when we come in tomorrow and look at putting it all together, you know what's going on. Okay? So I'm going to mute my mic. If you need help, let me know. If you want to take off, that's fine. I'm okay with that today.